So the current topic is electric current in conductors. Electric current in conductors. See, let us define what is a current first. So in the previous chapter we have studied charges at rest. So in this chapter we will study about moving charges. Moving charges constitute current. So you can consider any metal, maybe metal in the, let us take a metal in the form of a cylinder. So this is the cylinder. So we know metal contains a lot of free electrons, and free electrons may be moving randomly in all possible directions. So you pick up any point, maybe this point, and let us make a small area here. Let's make a small area here. Now let us calculate number of electrons that are crossing this area in this direction. Let us calculate net electrons that are crossing this area in this direction. So when you compute net electrons that are crossing this area in this direction, you get 0, because electrons are moving randomly in all directions here. So when electrons are moving randomly in all directions, at any point if you compute net charge flow through this area in any direction must be 0, because the same amount of electrons will go in opposite direction also. Because of that, net charges going through this area in particular direction will be 0. So then there will be no net current. But when you apply for the same conductor, when you apply an electric field in this direction, let us make the same area once again. Then when you apply electric field here, then electrons will be experienced by force. Because of that force, then electrons will try to go against to this electric field. So many electrons will go in this direction and less number of electrons will go in that direction. When you compute net flow, you see net flow in this direction. Let's say if delta Q is net flow through this area in this direction, and let's say this is a number of charged particles that are, this is total number of charge that is going through this area in this direction in delta t time, let us say, then you can write down current as the rate of flow of charge. So you can write down delta Q over delta T is, that's I, right? So this delta Q by delta T equals to, that's current, and to define instantaneous current, I can write down that as limit delta t tends to 0 and delta Q by delta T, and when delta t tends to 0, delta Q by delta T can be written as dq by dt. So now current is defined as rate of flow of charged particles through the rate of flow of charge through this area. Right? So the rate of flow of charge may be constant, may not be constant. For example, if you take a battery and when you connect battery to the conductor, then you will see a constant flow of charges through any area, so you get current constant. In case of lightning, you don't get constant flow of charge, constant rate of flow of charge. The rate of flow of charge may change, the rate of flow of charge may change with time. So you don't get constant current. But when you connect a battery to this, you will get constant current, right? So now this is what current is. So this is a scalar quantity. It's not a vector, because this is the defined as dq dt, and dq is a scalar and dt is also a scalar, so you get current scalar, right? For example, if you take two wires, so one wire is this and one wire is this. If I1 is current carried by first wire and I2 is current carried by second wire, if it's a vector but you don't see anything, for example, if there are two vector quantities, let us say one F1 and one is F2, then if two forces are acting at a single point in this direction, in that direction, but you will see the net force in this direction. But here, if current is going in this direction and in that direction, the net current cannot go in this direction. This is wrong. So because of this reason, you say current is a scalar quantity, current is not a vector quantity. And let us define one more parameter called current density. Current density. So current density is defined as, it's a vector quantity once again. It's defined as J equals to I by A. It's a current through unit area. For example, you take a metal, once again, you take a metal. Let us take a small area here. Let's take a small area. Maybe ds is the area, or dA may be area. Area of this one is, say, dA. And if current going through this area is, let's say, I, then here you can define current density as I by dA. I by dA. And for this is average density. For instantaneous, you can write down as limit delta A tends to 0, then I by dA. That's what your current density. For example, if the area is making some angle with the current direction, let us look at this one. This is the conductor, and if this is the area, let us say, so this is the direction of area, then current is flowing in this direction, let us say, then angle is theta, then in this case the current density is written as I by dA cosine theta, because you can break this one dA into two parts. One will be along this direction and one will be along that direction. The area along this direction will be dA cosine theta. That's what you have to take. So this is what current density. And look at, current density is a scale vector quantity, and area is also a vector quantity, but current is a scalar quantity. So you can also write down that as I equals to J dot A. So like your flux, so we wrote that flux equals to E dot A, because E is a vector, A is also a vector, and phi is a scalar. Similarly, this one, this is amount of charge that is flowing through the area per unit time. So this is what the link between current and current density.